Thanks, everyone, and thank you to our first speaker for their very insightful talk. So now we're going to be moving on to a discussion panel based around the Schmidt Fellows and their different carpentries that we have created to work collaboratively across disciplines. So first, I want to briefly talk about the Eric and Wendy Schmidt Foundation and the AI Fellowship more generally. Bill gave a very good introduction to the fellowship this morning, but these are two quotes that I've taken from their website that highlight that the adoption of AI in scientific and engineering research is slow, unevenly distributed, and inconsistent. And the ethos of the Eric and Wendy Schmidt Fellowship is kind of that AI research has been mainly focused in biomedical research and computer science research, and hasn't really been given a lot of funding across like broader scientific domains. So the fellowship that they've created was for people from any background that wasn't biomedical science or computer science. And so they've created this fellowship, as Bill said, it's across 8 universities with about 10 fellows each year for the next 5 years. So because of the disciplines that they're trying to address within the fellowship, everyone in the fellowship comes from a different background. We have a lot of people in the 10 fellows at this university from more scientific backgrounds, and they're from domains where AI isn't traditionally used in the research. So we have people from chemistry, evolutionary biology, environmental science, disciplines where AI wasn't really the main methodologies used in previous research. And then we have other fellows that come from more of a computer science background, from data sciences or from computer sciences, whereas they have less exposure to applying these AI methods to scientific questions. So therefore, the Schmidt Fellows as a collective, and as well as the wider AI research, is going to work best when we collaborate together and we draw from our discipline knowledge, our domain knowledge, and our AI knowledge. So you may have seen the title of this talk, talking about carpentries, and thought, what is that? So Carpentry is basically a working group that we have formed based on a similar research interest that we have in the group. So as I said, we all come from different backgrounds, so we all have different methods that we're going to be using, but there's actually quite a lot of overlap that we'll see in a bit. So we basically form these working groups in which we can meet and discuss regularly any problems we're having, any questions that we have, so we can collaboratively talk and discuss and move our research forward together, despite coming from these opposite disciplines. So we meet weekly, as I've said, and we've been recording our work. So we meet and we do little workshops, mini workshops for an hour or two, and we've been recording these. And once we've tidied these up, we're going to make these data available and these coding resources available so other people can learn from our experiences. And the carpentries aren't just for the AI fellows, and we really want other people to get involved. So this talk that we're doing now is going to give a little bit of flavor of 3 of the carpentries and try to encourage people to engage and interact with them. So the first carpentry that we'll be talking about is the new to AI carpentry, and it's called the new to AI carpentry for a lack of a better term. Basically, this is the carpentry for people that came from a non-AI discipline background. So these are the scientists that are now moving towards applying AI to their research, where previously they had little exposure, or they've just used off-the-shelf methods such as like Google Vision and things like that. So I just want to introduce the panel for this session. So I'm Dr. Nathan Fox. I'm an environmental scientist, and I'm looking at using artificial intelligence for crowdsourcing data from social media to monitor biodiversity. If the rest of the panel would like to introduce themselves.
I'm James. I'm an evolutionary biologist, and I'm going to be trying to apply deep learning to understand complex morphological evolution.
Everyone, thank you very much for joining us today. My name is Anastasia Visharatina, and I'm from Department of Chemical Engineering, and I work on application of AI to nanoscience, and in particular for development and design of novel advanced functional nanomaterials and devices.
Hi, everyone. My name is Predi. I'm from the Department of Chemistry, particularly computational chemistry. And here I'm going to use machine learning to improve or create new density functionals so that we can calculate the energies and properties of molecules that are generally challenging.
My name is Xin Xie. I'm from the Department of Physics. I'm working on the deep learning for the inverse design of topological photonic system.
Thank you. So I just have a brief couple of slides and then we'll get on to talking to the panel. So we've all come from different backgrounds, as you've just heard. And the reason we've chosen to apply for this fellowship and apply AI to our research as opposed to the traditional methods, actually, when we got together during our first carpentry and had a discussion, we were having very similar ideas and reasonings behind why we need to use AI. So the things that have already been covered in the previous talk, such as big data and scalability of research, to more efficient computing. I'm not going to go over these too much because we can ask the panel a bit more about their opinions on these topics. But the thing I want to highlight is these three images in particular. So a photo of a whale, a 3D image of a skull, and then a nanoparticle. So a lot of you will probably be thinking, oh, those research domains are very completely different. There can't be any commonality between your methods or research interests. Well, actually, all three of these disciplines and the three fellows in this carpentry actually all have very similar research interests in using computer vision. For example, I want to be able to use computer vision to identify and label species, as we've seen in the previous talk. James is interested in using it to identify and label features on 3D images. And Anastasia is looking at identifying chilarity in different nanoparticles. So actually, despite coming from three very distinct disciplines, we have a very similar methods. The methods aren't going to be completely the same, but the basic architecture and the problems will be. So as I said, we share very similar research interests. And we've also discovered that we also share very similar AI challenges in implementing our work. So some big challenges that we personally have realized is that there's data scarcity and acquisition, which leads to poor models. There's a lack of computing power to carry out the research we want. And then we've also had broader discussions about data and privacy, about our data, and also the ethical considerations. So as these challenges are shared across all of our disciplines, it actually enables us to work together despite being from different disciplines to find cross-cutting solutions to our challenges. So that's the brief introduction to this panel. And to start off, I would like to ask the panel to explain why they believe that using AI for their research is going to be much more useful than the traditional tools used in their discipline.
Yeah, I would like to talk about that. So in chemistry, so we try to simulate the reactions before it even happens. Sometimes you want to know if a catalyst is a good enough catalyst before you do the reaction. You want to try out by simulating them computationally. Now, to do that, you need to calculate the energies of those systems and other properties. And that problem gets harder and harder as you go to more complex chemical systems with more number of electrons. That is because of the electron-electron correlation, which is very hard to calculate analytically. So there is a theory called density functional theory, which enables you to do that rather easily. If you know the electron density of a system, you can calculate any property of a chemical system. But density functional theory just gives you that theorem. We don't know how analytically the electron density is related to the energy. So that is where we can use machine learning to map the electron density of a chemical system to its properties, or specifically energies.
So I can. So the scientific part of my research focus on the manipulation of light behavior in nanostructures. So the most important part is to design the nanostructures with desired optical properties. So the traditional method, which is a combination of numerical simulation and optimization algorithm, that's traditional method not only requires a huge computational cost, but also offers no clear strategy to optimize, especially for the design task with multiple desired optical properties. So the AI method with the data-driven method may provide an efficient route to fully explore the design space and realize on-demand design with more efficiency.
To speak more a little bit of nanoscience, and I firmly believe that application of AI to nanoscience will greatly benefit both fields because it will also help to design and develop some new structures faster, but also perform their characterization and post-processing analysis of these particles. So all stages of this pipeline will be significantly accelerated and get more ideas how we can get more materials. And in particular, for example, for semiconductors, for example, it will help us to develop new electronic devices, and then it will help to get more powerful computers to train and large models and then repeat the cycle. But also, as we know that potential of nanoscience is go far beyond of electronics, and as an example of COVID, mRNA vaccines. And so application of AI to nanoscience will enable greater opportunities for electronics, photonics, and healthcare.
Great, thank you. And then the second question that I have for you all is, based on coming from a domain science background, how easy has it been to learn these AI methods, and what educational tools do you think are accessible for other people to use?
I think the biggest challenge for me personally has been trying to learn like this vast field of artificial intelligence, machine learning, deep learning, knowing what the best method is to use, because there is no sort of guiding principle in evolutionary biology. Very few evolutionary biologists use machine learning or artificial intelligence, or more specifically deep learning. We are like regression is technically machine learning. So I think trying to determine what the best neural network to use has been a big challenge. And as part of that, because I'm not so comfortable coding in Python and some of these other languages where the architectures are actually implemented, it makes it very slow to develop a pipeline that can then be applied to my data set. So it's hard to evaluate whether the approach I'm taking is easy. And so I think for me, that has been the largest challenge. And of course, because there's so many new research avenues in deep learning and machine learning, it's difficult to keep up with it. You guys have?
Yeah.
Should we open it to the crowd?
Yeah, and then I was just going to add on to that. Actually, these Carpentries have been one of the best learning avenues. There's all of these online tutorials, things like Coursera, things like that, and they're very useful for like broad overviews, but actually like the hands-on approach and working together across the disciplines has been very helpful. And I think the learning rate that we've achieved working in a group of 5-6 people for an hour or so every week has helped us grow and learn these methods a lot quicker than you would be on an individual scale. So if there is anyone in the audience that has any questions about how to get involved in AI research and how to form some interdisciplinary teams, we'll open the questions to the audience.
So you mentioned how your background wasn't necessarily programming in Python and how that's been like a barrier, and that's very well aligned with what I've seen trying to figure out ways to teach how to use these methods like to other folks. I guess I was curious how many of you in maybe your sort of background disciplines were learning Python, and also do you have any thoughts about what would be the effective ways to give people Python literacy quickly for specifically this reason?
I can answer that. So actually, when I said we didn't have a better term for new to AI, it's none of us had any experience in Python. And we wanted to be able to go from entry-level Python experience to being able to do deep learning. So some of us had no coding experience. I did all of my work in R, and I'm very comfortable in R, but R has limited capacity for running these big models efficiently. So the point is moving from this entry level of, oh, we know a bit of coding, or we know no coding, or we know very basic intro, hello world, Python, to moving to deep learning at a quick rate, because we've been in this for 3 months now, and we've been working at it for 3 months. I think there's a lot out there, and a lot of it isn't relevant, and a lot of it is just the courses online can be confusing and not accessible. They assume a high level of knowledge. So I think working with other people and not being afraid to ask questions is probably the best approach. So like I said, we've been putting together all of the notes from our previous meetings. So we have this entire like Google Collab that we've started from scratch, and within 3 months, we've already started building deep learning models. So we have this resource that we're going to fine tune and make a bit more accessible. But I think, yeah, I think it's a bit of a difficult challenge to approach.
Really quick follow-up. So there's this whole other barrier that we found between being able to build this code in Python in something like a Google Colab or a Jupyter Notebook, versus then moving to Python scripting, which particularly when you're trying to scale up, if you have a model that's not going to be able to train on Colab dependably because it needs to be able to train for 3 or 4 days, that actually just getting to the point where you're moving to this idea of the command line and scripting and like going from Colab to something with larger scale, we also found was like a huge increase in complexity. Because if you're used to doing R or MATLAB, you can download a package and it's kind of enclosed, and you're not thinking about things like resource management and, you know, running stuff from the command line. So I guess I'm curious if any of you have hit the point yet where Colab is insufficient for your needs for the models you're building.
Yeah, so I think we're all like haven't really got into the intensive training yet. We're still learning. I think we haven't reached that point yet. But yeah, it's a good point that we really appreciate that. So we'll take it into account while going forward.
Yeah, I can speak on that. So I'm one of the AI fellows, and my background is in computational fluid dynamics. So scripting and developing code is really something I've worked on for a long time. And thinking about, I came from this Aero group, and a lot of these new PhDs, it's a hurdle that you need to overcome. And while I haven't done any training, I'm thinking of maybe organizing something like that in the summer. I think like a crash course, 2-3 days, and thinking of it from a really applied side, because a lot of us researchers, we don't need to be code developers. We don't need to know all the details, but we need to know where to start. And I think sort of a crash course with someone who's gone through it, works on similar systems, I think can really get people up to speed. Because it's really daunting when you don't know anything. You go to Stack Exchange or something, and there's a lot of jargon. But if someone who's kind of gotten through that can just simplify it and say, this is where you get started, I think you can really speed things up.
I just like a very small comments, because in my field, people use some coding for their needs, like not necessarily for neural networks, but like just for something like processing of their data. And I believe like since AI now hugely transforming science and engineering, I believe that universities should incorporate more structured courses during undergrad and graduate school, so students can implement all of these things during their studies and already have this experience.
So if I could offer a very practical suggestion, I was sort of in similar shoes. I'm trained as an applied mathematician and got into this about 5 years ago. And that's to take advantage of the resource of the amazing undergraduates that we have here. Many of them are really amazing Python coders, and it's really easy and in fact good to get them involved in your research projects. And as I code along with them, I've had to learn very quickly on the fly. Or right now I'm teaching a course in machine learning in the math department, and I had to use Python. And as you're coding in front of the class, I could assure you, if you mess up, the students will let you know. Yeah, I mean, we have some really amazing students. You have some amazing domain knowledge, plus also the experience of having a PhD, knowing how to write papers, how to put together a scientific project. So if you work with some of those undergrads, you'd be amazed. At least I'm amazed. That's taught me a lot quicker than Coursera or things like that.
Great, thank you.
Thank you. Okay, we're out of time for the New to AI panel. So anyone that has any further questions can talk to us during the networking session at lunchtime or in the evening. So next, I'd like to welcome to the podium James, who will introduce the next Carpentry. And if you're interested, our email address is here and it will be on a couple more slides. And the New to AI Carpentry meets on Wednesdays from 3 till 4 regularly, but we can do ad hoc sessions and meet with other people outside of those times as well.
There we go. Cool. So I'm really excited to introduce the deep learning carpentry. We're a little bit behind, so I'll try to get through it quickly. But we have a couple new panelists, Yutong and Jennifer, if you would like to introduce yourselves.
Hi, I'm Jennifer Lee. I'm from the astronomy department, and my science area is studying the physical property of supermassive black holes in large astronomy surveys.
Hi, I'm Yutong. I'm from the Department of Electrical and Computer Engineering. I work on theory for deep learning, and I also work on reconstructive spectroscopy for wearable devices.
Cool. So the goal of this carpentry is to rigorously apply deep learning methods to our engineering and scientific domains. And often for us, that means sort of thinking about the limitations of the current implementations and trying to move past them. So the sort of first question is why deep learning at all? And we're at a time where the availability and maturity of deep learning libraries like PyTorch and TensorFlow are really good. So you can, once you're proficient in these libraries and in Python, you can pretty rapidly develop and deploy models, test into your data. And working in a carpentry is obviously very useful in this setting because we can run it by each other, debug together, all of this sort of thing. And if all we had was well-developed libraries, we probably wouldn't have a whole working group dedicated to the subject. So the other, though broad, reason that we're interested in deep learning is that they tend to work better than shallower methods. Theoretically, it's not exactly clear why this should be the case. But a couple of the things that it does do well is when you're dealing with complex data, it can learn sort of underlying features, perhaps due to the manifold hypothesis, and it has this incredible expressivity. So they're very parameter-rich models, but it allows a lot of customization and can be applied in domain-specific ways. That's why we use deep learning. A couple of existing applications. I'll try not to butcher the science too much. This is out of my domain, but the basic idea is that you can create these structures, whether it be photonic or nanoparticles that have particular properties. And the way that we have gone about developing these particles, which are really useful in all sorts of applications, whether it be the screens you're looking at or the information that we're getting through, wires. The reason that the way we usually go about this is that we have some sort of basic physics knowledge of how these particles are going to interact with the structures that we're trying to design. And you would create a structure, test its property, and do this repeatedly. With deep learning, we can do something called solve the inverse problem, which is that we have a desired property, and then we can try to design the structure based off that desired property. And so that's a big application, and some of our fellows are interested in exactly this type of problem. Something from my domain is this deep learning on butterfly phenotypes to test the oldest mathematical model in evolution. This is the Mullerian mimicry, which is just this idea that species which have some sort of poisonous component often have a display to warn predators like, don't eat me. But these displays, the predator has to learn to associate the display or the coloration, in this case, the butterflies, with the fact that they're poisonous, stay away, cool. What's interesting is that often species that have poisonous components will begin to mimic each other's appearance. And this is so that the predator doesn't have to just learn off of one species, it can learn off any of the species that have this particular phenotype, so this coloration. This was really interesting because we often lack the tools in evolutionary biology to quantify very precisely what the phenotype of this is. This is obviously an image. It's very difficult to quantify exactly what the image is. And so they applied convolutional neural networks, a pretty standard computer vision technique, to show that, yes, these things are convergently similar. So finally, we'll talk about some of the limitations, which Dr. Beery already discussed a little bit in her talk. So the first is reproducibility. We've seen reproducibility crises in scientific fields fairly recently, and it doesn't seem like deep learning is going to help with that. So there's a lot of variability that when it comes to initializing the models and tuning the hyperparameters, random seeds. So that's a concern of ours. Computational equity was touched upon. So the funding for academia and the computational resources available in academia are a drop in the ocean compared to what industry has. And so this might slow deep learning development. Wheels get reinvented a lot. So in academic settings, we're often replicating each other's works, just we think possibly because we don't have such a set of domain-specific resources available. Explainability, I won't talk too much about this because our next Carpentry is going to be about explainability in AI. But the basic idea is that these deep models are complete black boxes. We don't know how the input data is being transformed into our output. And as scientists and engineers, we're often very interested in how that transformation takes place. And then finally, they're data hungry. And this has to do with equity, where we can't collect data on the scale as a lot of industries, but we also don't have that kind of data available very often as scientists and engineers. And so I know that's a little negative, but maybe we can talk about a success story in a scientific domain and ask Jennifer to talk about how astronomy has overcome some of these limitations.
Okay, yeah, I wouldn't say astronomy has overcome the entire situation, but this is like something I've been observing in my field, and I really thought that was really interesting. So like in many other domain fields, like data acquisition and data collection is very expensive. For example, you have a very expensive simulation to run, or you have like you have to build all these like cameras or like instruments and stuff like that. So same in astronomy, right? Like not every university or any like research group can launch their own space telescope, right? And so like it is very important for us to like really share the data among the community. So like in astronomy, many different national level research institutes, like for example, NASA or like the Space Telescope Science Institute are trying to share the data within the community. So what they do is actually they host all the old archival data on platforms like Jupyter Hub or like Google Colab, so that people can really use the data no matter what institute you're from. And so these labs also like host tutorial sessions so that people can learn how to access the data easily. And so this is like touch upon like what we were just talking about, how to like share data and also how to like teach everyone to use these data and models. Yeah. And so this is kind of like a new initiative in astronomy. This is a way where we want to share our data. We want to keep our models as explainable and as like transparent as possible. And also finally to promote equity in the field of astronomy.
So we can open it up to any questions. Anastasia, I found you.
Thank you.
No? Okay, then I have a question for Yusong, who holds a somewhat controversial opinion that perhaps science and academics in general should focus on questions that can be solved on a laptop. Would you care to expand on?
Sure. So in my PhD, I worked on mostly shallow methods, like methods that you can, like support vector machine, things you learn about in like introduction to machine learning, at least like a few years ago. But I think nowadays when you take introduction to machine learning, a lot of it is deep learning. But I think a very important principle to like always keep in mind, like for our carpentry, when we talk about all of our problems, is like before we try deep learning, can we try it on like the simplest model possible and see if that give us any result. So I think like my opinion that you should do research that only works on your laptop is more like tongue in cheek, but it's really just to say maybe we should like look at what is the limitations, like do we truly understand the limitations of shallow model, and then maybe then we can understand what is why deep models actually can circumvent those, because there's a lot of characteristics of deep learning that actually can be replicated in shallow model. So as scientists and engineers, we should really work hard to understand what exactly set them apart and when to use them and how to use them responsibly.
Yeah.
Is it on? Speaking on what you just said, I had a project, so I'm towards the end of my PhD. I had a project using a random forest for the explicit reason you just had was, do we understand the limitations of these simpler models before you want to apply it to deep learning? And when I submitted my paper, one of the reviewers would not allow the paper to go through without me comparing it to a neural network. And I just found that fascinating how at least in that field, or at least maybe it was just that one reviewer, they almost don't even care about the more simple models at this point. People are very much just gung-ho on as deep a neural network and as many different types of GANs and all these wonderful things that can do amazing things, especially in our field, my field, or system science. But at the same time, it feels like we've kind of skipped over that early step, and I see it too. I just wanted to share that.
Yeah, that's really interesting, because I often wonder if deep learning will one day become the gold standard for all of our fields. I don't see it in evolutionary biology yet, but maybe one day it'll be the same kind of thing where it's like, oh no, you haven't done the right method, you have to use deep learning. And I wonder if maybe the other panelists think the same thing of their fields, where one day these simpler, shallow methods will just be outright replaced by deep learning methods.
Yeah.
Oh, yeah, sorry.
Just to follow up on that,
Yeah.
I just don't understand why we would want to have more complicated things for something that a simple machine learning method can solve for us. And like you said, maybe run it on a laptop instead of on a cluster of GPUs. It just seems like the more simple approach is usually the best, in my opinion. But
Yeah, I think at least in chemistry, what I've seen is it's very problem specific. There's a data problem in chemistry, like you need big data to do deep learning. So if you are trying to predict the outcome of a reaction, let's say you put like this, whether reactant A will give this much yield when it reacts with reactant B, and problems like that, you hardly have like hundreds of data set. Like you have hundreds of examples in the data set. So in that case, I've only seen like random forest, or mostly like shallow learning methods in such cases.
So I think that's it. I'd like to maybe welcome Bernardo and Andreas to the podium to introduce our final carpentry and final panel discussion.
All right. Next, as our panelists get seated, I want to introduce the Explainable AI Carpentry, where we're interested in improving trustworthiness of data-driven modeling for science and engineering. So I want to introduce some of our carpentry members, Yossi Cohen in mechanical engineering, who unfortunately couldn't be here today, researching responsible AI. And you have met Jennifer Lee. I'm Andreas Rauch. I came from aerospace and I work on flow simulation. I'm interested in data simulation and machine learning techniques. And Bernardo?
I'm Bernardo Modenesi. I'm a data science postdoc, not Schmidt postdoc, but we work together nonetheless. I come from the economics department and I have a degree in, I have a degree also in statistics, and I've been researching ethical AI models, metrics, and developing ethical AI metrics, and also causal inference models combined with AI.
You all met James and Yutong, and two other Midas Data Science Fellows are Maria Han Vega in mathematics and Efrain Cruz Cortez studying complex systems. So we all know the massive interest there is in using AI, but with this come lots of different stakeholders that want to use AI or have a certain perspective on it. And be this the industrial perspective, a regulatory perspective, the end user, or the stakeholders probably closest to us, the scientific and the developmental perspective. There's this huge demand for trustworthy and explainable AI. And often AI models, these deep neural nets, are seen as black boxes, where we map from inputs to outputs, but it is not understood or very difficult to understand what's actually happening inside this model. So our goal is to move towards a glass box model, which we see as being more explainable or completely transparent, where we understand what is going on inside the model and how we go from our inputs to our outputs. And this is why we see explainable AI as critical, to make interpretable, data-driven modeling that establishes trust at the interface of decision makers and intelligence systems. And I'll hand off to Bernardo. Oh, sorry, one more slide for me. We want to explore this based on a case study on turbofan engine prognostics. And turbofans are pretty much standard in every commercial flight you'll ever get on. And here we have this map of the stakeholders again. There's the people with the domain knowledge, the engineers and the scientists. There's, of course, air traffic regulations to ensure safety for passengers. There's commercial airlines that have obviously an interest in keeping everyone safe, but also to remain economically viable. We have both the engineers that develop these and also the end users that want to trust that we are making good decisions and that we are flying these planes and these engines safely. And then lastly, the people that make these day-to-day decisions. They need tools that they can trust and understand to make responsible decisions. And we see this case study as an excellent application for multidisciplinary brainstorming, all of us panelists coming from different domain fields. And the goal of turbofan engine prognostics is to save lives, reduce costs, and also advance science and industry.
Thank you, Andreas. So we chose this example because it's something we've been working on the Carpentry. Actually, it's one of the projects from Yossi that we've been working together in the Carpentry. We're analyzing and we're trying to predict the remaining useful life of these turbofan engines and also some types of failure modes these engines can have simultaneously. So what we do is we fit in, related to the deep learning Carpentry, we fit a neural network with real-time sensor measurements of these turbofan engines. We have 129 features and we have a neural net to predict 7 outcomes at once. One of them being the current health state of the engine, 5 of them being the types of or modes of failure or types of failure this engine can have. And the last one, the remaining useful life of that engine, which is useful for airlines to monitor and know when these engines are going to fail and design better engines as well. And for this specific talk, we're going to focus on the remaining useful life of the engine, the last outcome, just to make things a little bit more simple and tell you the intuition that we have and the goals we have with this Carpentry. So first we predict with the neural net, and then second, with the remaining useful life of the engine, we want to understand how is the model making that prediction. Or in other words, we want to make the model a little less of a black box. We want to understand a little bit better. And for that, we employ Shapley values, which is a metric widely used in explainable AI field, which tells us how the marginal contribution of each of the 129 features to the final outcome, to how, what's the, to the remaining useful life of the engine. So we calculate these Shapley values for all the 129 features, and actually we can calculate even for each observation, the marginal contribution of each feature to the remaining useful life. And here we plotted, we selected the 10 most important features or the most impactful features on the remaining useful life of the engine. And interestingly, we realized that the cycle of the engine, the number of cycles, which is kind of the odometer of your engine, is really important. It's the second most important feature to predict remaining useful life of the engine. But surprisingly, the pressure at the low pressure turbine is even more important on average to predict the remaining useful life of the engine. And that was unexpected. And that's kind of puzzling. And we're going to come back to that puzzle in a little while. But before going to that puzzle, we want to also, I have to tell you something. These Shapley values actually are not the exact Shapley values because the Shapley values, the exact Shapley values are infeasible to be computed. We have it's in this application specifically. So we do a random approximation of these Shapley values. So with that comes a little bit of uncertainty, right? So we move on into quantifying this uncertainty, which is also a topic in this carpentry, uncertainty quantification. So we want to know, okay, we can explain the model or we can understand a little bit better how the model makes predictions in terms of remaining useful life, but how certain are we about the contribution of each feature to the remaining useful life of the engine? So we run some Monte Carlo Shapley estimates to quantify this uncertainty or the variance of each feature's contribution to the remaining useful life of the engine. And with that, we produce some confidence intervals of the Shapley values, or we understand a little bit better how certain or uncertain we are about our measurements of how features impact the remaining useful life of the engine. And so we first fit our model. We did the deep learning task. Second, we tried to understand how the model is making the predictions, which is using Shapley values. Third, now we quantify how certain we are about our predictions or explainable tools that we're employing. And third, now we want to move to the last point of this carpentry, which is to try to understand the world or the science or the theory that goes beyond the model. The model sometimes captures some correlations, but they are not necessarily the true correlations. It could be just out of randomness in our data. So here I talked about the puzzle before, that the low pressure at the low pressure turbine, the pressure at the low pressure turbine is more important than the number of cycles an engine has to predict the remaining useful life. But that's kind of puzzling. What can we learn from that? So a little bit pushing back on Yutong's opinion on doing your research on a laptop, maybe this deep learning can generate puzzling hypotheses for us to be tested. And that's the last point of our carpentry. We're learning and trying to employ causal inference to test hypotheses that come out of these models, so we can understand a little bit better about the world. We can design experiments to learn, for example, how is the pressure at the low pressure turbine contributing to the remaining useful life of the engine. And yeah, in this carpentry, this is actually a fusion of two carpentries that we're presenting now. We have uncertainty quantification, explainable AI tools. We study causal inference as well, and all with the goal of making these AI models a little bit more interpretable, more trustworthy, and also to see what we can learn out of these models. yeah, we meet every Wednesdays from 3 to 5. You're welcome to join us, and we can start maybe a discussion talking about how explainable AI tools or causal inference tools can be helpful or not in your research.
Yeah, I can start. So I, like I mentioned, do flow simulations and modeling. And machine learning tools are getting more popular in these fields to either supplement analytical models or entirely replace them if you can. But we can't get around this problem of when we move outside of the training regime, apply it to a different configuration, a different flow, the predictions are inaccurate or very difficult to understand. And I think a tool like Shapley estimates can bring some physics understanding back into your deep learning model. And then we can use that to interrogate the models and develop better ones.
Thank you.
I can also comment on that. So I'm from like astronomy background. And so for me, my research questions, the most important thing I want to understand is what is the physics process like lying in my data, right? So specifically, I study the light variability from supermassive black holes. And so the key point of my research problem is not trying to model the variability precisely, like it would, that as we observe, but exactly like what is driving the the variability that we observe in the light curves of these supermassive black holes. So for me, like explainable AI is really learning the physics behind the data we are seeing, not just like trying to like simulate the data.
Yeah, that's good. Yeah, for me, I take usually a slightly different path. I not only develop metrics for explainable, local and global explainable AI models, but I also use causal inference and combine them with AI tools in order to give intuition and meaning to AI parameters that are otherwise kind of meaningless or just nuisance parameters. That's one way to make them also more explainable. And I would also like to talk about the danger maybe of not considering explainable tools or even uncertainty quantification in our models. And as we were preparing this presentation, we were talking about imaging diagnostics in medicine. There is a paper showing that they train a neural net to predict, to detect cancer from images. And the neural net has astonishing accuracy in predicting cancer. And when the researchers were checking what is going on, how is the model making the prediction? And in other words, how can we apply these explainable AI tools? And they actually saw that the model was predicting cancer based on pen marks on the images, not actually learning the patterns of cancer. So in this is one way that explainable AI tools can be super helpful to make sure we're doing responsible AI. Another also example that we actually from a paper we read in the Carpentry that was showing that in the self-driving cars, a lot of the models they use, they do not embed uncertainty quantification. So some of the decisions that cars can make, automatic decisions, can be tragic. So this paper from Europe's 2017, it shows that sometimes when the model is not, we can quantify the uncertainty of the model. When the model is not too certain about a certain decision, it should just not make, because it can have some bad consequences. But I think with that, we can open, I think, to the broad discussion. If anyone has a question, have a couple more minutes.
Hi, I had a question about when you were discussing explainable AI being used to understand which features contribute the most to the result prediction. Are you taking into consideration the bias that might be in the data set? Because if it belongs to like a specific population, for example, talking about cancer, skin cancer,
Yeah.
if it's mostly from like the white population and then other people are not considered, then explainable AI would tell you what features are used for like that particular population, and it may not be the same case for other people too. So do you think it can find out the bias in the data sets and also tell you about that, or just the features that contribute the most to decision making?
Yeah, no, thanks for your question. Absolutely, that's a big point of concern in right now in the ethical AI field. I think for the turbofan engines, this is a little less of a concern because it can be biased, maybe depending on which engine you're observing. But in social sciences, I'm a social scientist. I'm an economist, and that is really problematic. And there are a few tools to make sure that you're maybe sampling a little bit more from minorities to have better representation, so the models do not have a higher error rate for minorities, for example. That's one of the ways to fix that. But there are also ways to check if after training, if your model is predicting in a undesirable way or harming some minorities. I'm also working with that. Yeah, so feel free to join us. That's a great question. And that's a really a big concern in ethical AI field.
Thank you.
If you have.
Yeah, maybe just to add to that, great question. As Bernardo said, he knows more about these tools to make sure minorities are represented. I think the Shapley in and of itself, it interrogates the model. So whatever biases you have in the training data, those aren't going to be, you're not going to weed that out alone with Shapley. But I think Shapley can then show you, combined with domain knowledge, do these feature contributions make sense? Or is this really strange, or should we look at it more?
Also, I want to shout out to Jag here, our director. He has some also project in protocols for making data sets more fair or to mitigate some of these problems of biases in data sets. So also, if you want to check his work out, yeah. Okay, question?
One moment.
Yeah, he's bringing the microphone.
Hi, thank you for the presentation. I had a question about uncertainty quantification.
Uh-huh.
Are you aware of any UQ techniques out there that give the uncertainty interval on prediction time? Because I feel like a big reason to use these AI models in an industrial context, like for, say, fault detection, real-time fault detection of equipment, you would want that interval at prediction time.
Yeah.
I know with like Monte Carlo dropout, it requires taking samples. So just curious, do you think the field is maybe that's a big knowledge gap in the field?
Probably, yeah. I see two avenues. One is that we have more computational power, so maybe we can do some dropouts pretty quick. But if we cannot do that, if you understand the nature of the problem, if you're observing similar structures, you can have some pre-trained models to inform you while you're trying to measure the Shapley values. You already have some idea of the uncertainty. You already have some pre-estimates of the uncertainty, not on the fly estimates. That would be maybe the closest you can get if you don't have computational power to do quick sampling. Yeah, but I'm not fully aware of on the fly uncertainty quantification. Yeah.
Me neither. That's all I wanted to ask. Thank you.
Maybe it's also like avoiding the field and a theoretical field that you can explore. Yeah.
Thank you very much.
I think we have one more. Getting your workout today.
Thank you. I just want to ask a question. It's kind of a two-part question, but do you think that the explainable AI is going to help with the trust deficit? So obviously a lot of people don't trust AI, maybe because they don't understand it, maybe because they just don't trust scientists. But do you think explainable AI is going to help with that? And the second part to my question is, how can you tailor these explainable AIs to talk to different people? So obviously domain experts are going to need more information than the general public, for example, but maybe the general public are the ones that have the biggest trust deficit with the AI model.
Does anyone want to?
I can talk a little bit about the first part. As an astronomer and physicist, like people in my field generally don't like these like deep learning methods because they think that you're operating on top of a black box, right? So this is something we talked about. And so like I say, like the really important thing is connecting your model results back into the physics that is behind the data you have. Yeah.
Yeah, I think this is one of the biggest challenges for academia to reach out and make a meaningful bridge with the public. Media is there, media outlets are there, but I think these tools can be helpful for us to, even for academics, to understand what the models are doing. I think not even us understand really well. They can help, but also even these explainable AI methods, they're not comprehensive enough. I think there are some gaps that as the literature advances, as the methods are advanced, I think we're gonna have better grasp and hopefully better way to communicate to the broader audience.
Real quick, I just want to add something real quick. I think the mistrust is a healthy mistrust. Like we definitely need that. And also a lot of the times I think like for really large models, even the designer themselves can't say with 100% certainty, like why it does certain things. So it's a really good thing that we have this mistrust and like it holds us accountable for pushing these forward. So maybe explainability is one avenue, and that's like a very productive philosophical stance, I think, towards what models should have, i.e. the explainability characteristic. So.
For the sake of time, we thank you for being here, and we're open also to talk more about it in our breaks and outside of it. You're more welcome to join us in our Carpentries. I think we're learning a lot, and also now even working on collaborations together, and it's really interesting. I'm an economist working with an engineer in a turbofan engine project, so that's really exciting. Please join us. Thank you so much.